All right, hello everyone. I'm Jacob Reher, and today I'm going to be talking about some of our recent work on realizing multi-contact locomotion on the humanoid robot Duris. And this was done in collaboration with several of my colleagues at the Amber Lab at Georgia Tech. So as our keynote yesterday very nicely put it, what we'd like to do is start taking a lot of these sci-fi type concepts, such as these NS5 robots that are bothering Will Smith, and trying to translate them into actual humanoid robots that we see in real life. So some of the areas that have kind of been identified as areas that we can start seeing that or want to start driving this towards would be like service robotics, disaster response, which was a huge motivator behind the recent DARPA Robotics Challenge, and exoskeletons or prosthetic devices where we can transfer human-like motions that we design on humanoid robots to devices, or robotic devices that are attached to humans. So here's two of the projects that we've worked on in our lab in the past. And one thing that we see as we work with a lot of these things is that, particularly with humanoid robots, they suffer from very high dimensionality. There's a large number of actuators and contact points and just general moving parts that are hard to accurately model and control. And with things such as our running robot here, which was the 2D prototype for our 3D humanoid that we're going to be talking about today, we're starting to have, with the more dynamic locomotion, more impact dynamics that we need to start considering in our models. We also have these underactuated domains that the robot's working in, such as the flight phase here, or what we're going to be talking about today with pivoting about tow. So with this goal of designing more dynamic and efficient locomotion that's more human-like, we can look at this metric that's been used in the locomotion community to classify the efficiency of locomotion. This is the cost of transport, or essentially the energy that you're using over the distance traveled. And we see humans ambulate with very efficient ease here, with a 0.2 cost of transport number. And some of the, in my opinion, the best walking that's human-like walking that's been implemented on a humanoid robot is the Petman robot here on the far right. But this is requiring a significant amount of off-board hydraulic actuation. And this number is not, we don't know for sure, it hasn't been released publicly, but it's been cited as being roughly 20. So past work in our lab has gotten a number of 1.3 on the same humanoid we're going to be talking about today. But what we'd really like to start considering is how can we design more dynamic behaviors and design these so that they're more starting to be driven towards the efficiency of a human while preserving some of our theoretical background. And we're not saying that we're particularly better than this yet, but what we'd like to do is try to use this combination of our theoretical background with an algorithmic approach to kind of design things in the future. So how this is going to shape out is we're going to design a hybrid system model for our system, and then we're going to transcribe that into a gate optimization that's going to give us a walking gate with some mathematical stability guarantees that we can directly try on hardware. So we're going to use hybrid systems as the underlying mathematical framework for our robot, and for this the contact points are going to determine the discrete dynamics of the system. And as the robot flows through various contact points, we're going to represent specifically human walking as this directed cycle here. And on the blue bubbles here, on the vertices of our graph, we're going to evolve according to the continuous dynamics of the system in each of the given domains. And these domains have pre-specified contact points for which we're going to constrain the continuous dynamics to evolve on. And as we change these contact points, or when we are hitting some guard function h, we're going to apply this discrete reset map or rigid impact relabeling matrix between on the edge of each of these vertices. So highlighted here in the red is the typical time that a human spends in each of these domains. So this is going to be kind of the nominal human cycle that we're going to try to achieve in this work. So when we're designing these walking motions, we'd like to begin with a reference trajectory. Here we have some human motion capture that we've done in the lab, but this could really be anything. We've also used Bezier polynomials in the past. What we'd like to do is take our robot and encode a set of outputs, or we term virtual constraints, that we would like to drive to this desired behavior. And if we can drive this, this difference, say, to 0 exponentially, then our robot's going to live on this reduced dimensional manifold we call the zero-dimensional manifold, or the zero dynamics manifold. And the problem really then becomes designing these gate parameters alpha such that we have this hybrid invariance. And what we'd like to do is then design these parameters so that we evolve along this continuous zero dynamics manifold. And when we strike and say we have an impact, we'd like to return nicely to our fixed point. So we're invariant through the impact map. And so what we'd like to do now is take this take this formulation and transcribe it into a gate optimization problem. So we use a direct collocation approach. In keeping with our theme of energy efficiency, our cost function is going to be the mechanical cost of transport. And with direct collocation, we're going to select throughout our continuous domains a series of cardinal nodes, which we're going to split the continuous domain into and introduce some defect variables that we're going to impose equality constraints on. And we're going to take this hybrid invariance that I talked about on the last slide and also encode it as a constraint on the system. And we're going to put all of these constraints into this vector C that our optimization is subject to. So with just a naive implementation of this and just using these constraints as we have them, we can converge to a walking gate, but it's not always necessarily amenable to actually walking on the hardware, despite it working in simulation. So here on the right, we have just trying this walking gate directly on the robot. And we can see that I can't let go of the robot, or it's going to fall pretty much immediately. So what we were seeing was we had some additional physical constraints that we felt we needed to append to these constraints on the optimization. And the nature of these optimization constraints means that we can easily append them to this vector. And the ones that we were seeing specifically was that the optimizer tries to leverage the torso movement in the walking gate, sometimes very aggressively. So we constrain the global orientation of the torso. Also, the impact velocity is sometimes very aggressive despite satisfying torque constraints in the joints. And we keep the swing legs well separated to avoid collision, and we keep the robot from pivoting about the stance foot by restricting the yaw moment in the foot. So the resulting walking is shown here. This was, as we run these optimizations, they converged in an average time of between 10 and 11 minutes, and this was just run on a laptop computer. So what we'd like to do is try to implement this on hardware while preserving as much of just this formal gate as we can. So as we had shown earlier, it doesn't necessarily always play back nicely just directly on the hardware. So what we'd like to do is just slightly perturb our formal walking gate with some global reference and use this to stabilize our walking gate. So what we have here for our global reference is an IMU in the torso of the robot, and we're using this to compute our floating base or our waist coordinate and modulate the hip joints accordingly. So we just have two modulations that we're applying. One is what we term a stance regulator, which is taking the stance leg or the stance hip of the robot and applying a torque to right the torso. We also have a swing leg regulator that is just adjusting the lateral foot placement of the robot if it sees that it's falling outwards. And as we adjust that lateral foot placement, what we see is that one of our virtual constraints, specifically the swing ankle world orientation, was very important with keeping the heel parallel to the ground. So we run an inverse kinematic solver to zero that virtual constraint. So we have the resulting walking here, where we can see a lot of the heel-toe action being played back on the robot. This walking had a step length of just under 0.4 meters, And we can see that there is some oscillations that weren't present in the earlier video. There was a significant amount of compliance in this robot. We use we're just correcting for that by assuming linear compliance in the hips, which is very similar to what I believe IHMC cited as using on the Atlas robot, and I believe others have used it as well. So the resulting walking was very efficient. We had a cost of transport of 1.02, which was over 30% more efficient than our flat-footed walking we had achieved in the past on the same robot. And as far as we've found, it's the most efficient walking that's been cited on a humanoid robot. We also had some quantifiable measure of human likeness. So if we view our graph as this discrete structure with weights, depending on, or with the duration that we spend in each of these domains, and we look at a data set of 8 human subjects, we can take the cut distance between this nominal human cycle that we had specified as our kind of goal earlier, and compare them with our Duris humanoid, and we see that Duris falls still within the range of natural human locomotion, at least within these 8 human subjects that we'd had found here. So with our dirty laundry, 10 minutes is still fairly long for these optimization problems, and the gates are still not immediately implementable on hardware. So we need to try to tighten this up. And additionally, these regulators that we're using to modulate the implementation is still a little heuristic. So we'd like to justify some of these results. We have some initial results with input to state stability, but we'd like to investigate this further or even apply a more formal controllers in this area. And full disclosure, every time we bring the robot up for this, to do this multi-contact walking, it takes a significant amount of time to tune in all of these biases and gains. And once we have it going, it'll walk for several minutes, say 1 to 2 minutes, before it needs human intervention to keep it from falling or hitting the edges of the treadmill. We also want to take this robot into more environments, say off of the treadmill or say out onto a sidewalk. We haven't done that yet, but we use the same methods that we presented in this work with a 2-domain walking gait, and we did take it around Georgia Tech's campus just under 2 weeks ago and got some walking with that. So I'm just going to leave that video playing while we take some questions.
Russ Tedrick is our first responder.
Thanks, Joel. So help me understand the energy argument here. So you say it's better than flat foot walking, and in the video I can clearly see heel strike, but I don't see toe off, which is what the dynamic walking community would say the biggest economic, energy economy benefit of doing heel toe walking is the push off, which would then reduce your future heel strike. Mm-hmm. I don't see that here. I don't see why the gait itself has changed the energy economy. I would, in fact, on this robot, I would expect the energy economy to be more dominated by the transmissions and other things like that. And did you put those in your optimization?
So the walking gait that we designed, in theory, will have this push off. And we saw that a few times throughout the experiment, but I agree in the video that we have here, the robot was beginning to, it kind of cycle or oscillates forward and back sometimes, so it's not as prevalent as what we see in the simulation. So when we were designing the walking gait, we were trying to leverage that domain towards the energy efficiency as much as we could. And I definitely agree, a lot of the energy efficiency that we're getting with this robot is coming from all of the gearboxes and the transmissions, and the fact that we're using very efficient motors. But I think another thing that we're leveraging is the fact that we have these passive springs in the ankles that are able to compress and absorb some of our impacts as well.
So what's the difference between the flat foot and this? I mean, can you explain the energy difference based on the foot?
So with the flat-footed walking, we're kind of limiting ourselves to the range of motion that we can have with the step length. So we have a much more crouched motion. If we're having the ability for the robot to toe off, even if it's not showing completely in the experiment, The fact that we have this toe off is allowing the optimizer to find gaits that have a much longer step length.
That makes sense. Awesome.
Thanks.
Yes. And actually, Lydia, maybe you want to go up and set up.
Yeah, great talk. Like, how does the hardware of your robot compare to that of a human body? Because I walked to the conference this morning and I didn't think at all about my walking. I didn't need 10 minutes of optimization at all. And do I have better hardware or do I have better software? What makes it so easy for me and so difficult for the robot to walk?
Yeah, that's a hard question to answer. I would say we have 15 just electric motors in the robot that humans have all these complex tendons and muscles and things like that. But one of the real challenges, especially with the walking that we're doing here, was we have no load cells in our feet, so we have no contact sensing with the environment. We're also doing all of this walking with no torque sensors in any of the joints. So we have essentially only kinematic information that we're operating on to get this walking. And humans have a lot of feedback with their environment. I say we use a lot in our locomotion.
Great, thank you. Thank you, Joel.